One of the nice things about numerics is that we can go to harder problems. Let's solve not the harmonic oscillator, but a pendulum. Okay, so a pendulum has we've got here a simple pendulum, so we've got a p squared on 2ml squared. ml squared is the moment of inertia. So if our point mass is swinging around our axis at an angle theta from the bottom, then its gravitational potential energy will be minus mgl cos theta. So there's my Hamiltonian, and here's my equations of motion. Again, I'm just taking the derivative of the Hamiltonian with respect to p theta and theta. And there are my equations of motion. Nice. One of the nice things about this is if I get my minus sign right up here, I get my minus sign all the way through. Again, this is trivial for such simple equations, but when you have big equations, that kind of thing really makes a difference. Okay, now we solve it just as we did before. Solution equals dsolve and crunch. Trouble. What's the trouble? The trouble is that Mathematica doesn't know how to solve those equations. It's trying to do analytic solutions to those equations, and it can't. Well, that's fair enough. Not all differential equations have analytic solutions. And like I said, if you want to really push the matter, you go look in obscure books, or if you want to push it even further, you go ask a very smart Russian, and that often fails, because that only really helps in the very boundary. So once Mathematica fails to do it analytically, what I tend to do is I tend to do it numerically. You can always plug the numbers in and see what happens. And it doesn't work particularly differently as far as I'm concerned, because I'm just making my pretty pictures anyway. So here's my code again. Now instead of using dsolve, I use that little n there. N stands for numerical. In dsolve, and you notice I'm making this solution a function of my initial conditions and my final time. And you look at the details of this and look up the help pages as I go. And now if I just check it, my answer is not some big analytic function. My answer is in fact a particular, because I put particular numbers in, my answer is a particular function of time. So what all this means is just I have a particular function of time. It says interpolating function because it's worked it out on particular points in time, and if I ask for the value at a time that isn't on that grid, then it will interpolate between and give me its best guess as an answer. And if I try and interpolate well outside this, if I try and ask what this value is for, say, t equals 100, it'll give me a guess, but the interpolation might go horribly wrong. So if you see your plots going fine for a while and then going crazy, it may well be that your interpolating function is, in other words, you solved it up to a certain amount of time and then you plotted it for a larger time. Okay, how do we plot it? Well, roughly the same way. We plug in our solution. This is a particular solution, so we're plugging a particular solution into a parametric plot. And just like before, we get some shape. And you see it looks pretty much like a circle. Okay. If we want to manipulate, we have to use slightly different language. So you'll see here we're using this wrapper evaluate around there. I recommend you don't worry about that. Just use it if you want to. If you get it's got to do with when various things are evaluated, and we want to force the issue in that case. But this works, in short. And so now I've got exactly the same thing. I've got a Tmax, and you see it's going beautifully around a circle, wrapping around it several times. And if I click on my locator, I can see the circle gets bigger, bigger, bigger. And actually, if I go out here, you can see it's doing something a bit more interesting. That's not a circle at all. Ah! Okay. And so now if I move around, you can see it's a circle, and then it gets a bit different, and then it does this. All right. This is, when you see this kind of behavior, you start thinking, all right, does this make sense? What's going on here? So let's remember our physical picture. Our physical picture is a pendulum. It's a mass on a massless stick swinging around an axle. So around here, it's going backwards and forwards, just like a simple harmonic oscillator. And indeed, for small angles, it is circular. It looks like a simple harmonic oscillator. As the angle gets bigger and bigger and bigger, and as the angle approaches pi and minus pi, then you can see it's starting to get very kind of sharp in these parts. And if I just make my time a little less intense, you can see that it's not getting as far. So it actually seems to be sort of stopping as it does that. Now what's going on? The answer is, as we get here, this point is where the oscillator is balanced up on its end, and it's just getting going, flying away. And so it flies over to the other one. And then it goes past and past. So it doesn't quite swing round. doesn't quite swing around, and we can see it doing that. So in here, it's actually just going forwards and backwards. But if we give it just a little kick near the upmost point, it doesn't go forwards and backwards. It just keeps going round and round and round. And that's it, going round and round and round in the two directions. Okay, so that all makes sense. One way of analyzing something like this, rather than just clicking around on this diagram forever, is to plot a lot of initial conditions at once. Okay, so what I've done here is I've made 100 copies of the solution, of particular solutions, and I've picked random initial starting positions. And then I'll just plot them all at once, and that will take a while, because it's plotting now 100 times what it used to plot, and I'll give each one of them a different color. So I'll just start at random positions in this XY plane. There we go. It's a different picture because they chose different random numbers, and you can see it's just spinning around, and you can see very much the structure here. Okay, let's ask ourselves some basic questions about this dynamics. Where are the stationary points? A stationary point is a point where if you start it there, it will stay there forever. And some of those stationary points are going to be stable, and some of those are going to be unstable. In other words, if you start really near one, some of them you're going to stay close, and the others you're going to fall away from them. So of the stationary points that you identify, which are stable and which are unstable?